Merhabalar. Öncelikle tekrardan bu organize eden arkadaşlara, Şefika'ya, Ceren'e ve Oğuz'a teşekkür edelim. Ege ile birlikte grid diyagramları ve NAT grupları üzerine çalıştık. Başlangıçta aslında biraz başka bir şeyler vardı aklımızda ama sonra böyle bir projenin aslında bu perspektiften çok incelenmediğini ve ilginç olabileceğini ve burayı biraz daha genişletebileceğimize karar verdik. Şimdi sözü Ege'ye vereyim. Kendisi Boğaziçi'nde matematik, fizik ikisini beraber götürüyor. Topolojiyle ilgileniyor. Buyur Ege.
Teşekkürler. Today I will introduce knot groups and show how we can compute knot groups by using two different methods. So, what is a knot to begin with? A knot is defined as a closed, non-self-intersecting curve that is embedded in R3. So the mathematical knot is not much different than the usual knot we are all used to. We just impose an additional condition that after tying a knot, you must connect its both ends together. So here is the picture of a simplest knot you can tie, simplest non-trivial knot you can tie. It's called Terrafoil. The usual way to represent knots is to project them onto the plane and specify the undercrossings at each crossing point. But obviously, it's not the only representation of that knot. Since we stated that our knots must be closed, I can take this diagram and deform it continuously, and resulting diagram would still represent the same knot. So any move that does not change the knot type can be represented as a certain combination of following three moves, which are called Ridermeister moves. So if we have a knot and we apply those three moves, the resulting diagram will still be the same, represent same knot. So here are the two pictures of the same knot, trefoil. One can be obtained by the other by applying the Ridermeister moves. But you can see here that it's difficult to see they are the same at the first sight. The right one has more crossings and seems very complicated. And that brings us to the main question: how can we distinguish two knots? And the usual strategy is to use knot invariants. A knot invariant is a quantity defined for each knot, which is the same for equivalent knots. A knot invariant might be a number, like linking number, might be a polynomial, Alexander polynomial, Jones polynomial, etc., or it can be a group. But the defining properties of them is that they do not change under the Ridermeister moves. So if we have two knots and they differ with respect to a knot invariant, they can't be the same. So what we do is usually to calculate knot invariance for specific knots. And the one I will talk about today is the knot group. But before giving the definition of a knot group, I must briefly describe what fundamental group of a space is. So suppose we have a topological space X. First, we fix a base point x0 in X and consider all the base loops in X. I mean, all loops that start and end at that base point. So, and then we define a composition of two loops in a very natural way. If you have two loops, L1 and L2, to get the composition of them, you first travel down the first one and then down the second. And we say that two paths are equivalent if one can be deformed continuously into the other. So with this setup, the collection of all loop classes forms a group with the composition as group operation. So basically, the fundamental group of a space X consists of all the loops that cannot be deformed into each other. So here's an example. On the surface of torus, there are only two loops that cannot be deformed into each other. And in this picture, they are denoted by A and B. Other than that, any loop in the surface of a torus can be represented as a certain combination of A and B. So we say that the fundamental group of torus is generated by two elements, A and B. And there is no relation between A and B, so that group will be a free group. Now I can define the knot group. A knot group of a knot K is defined as the fundamental group of its complement in R3. So to compute the knot group, we first drill the K knot out of the R3 and compute the fundamental group of the remaining space. And the first method I will show you is the Wirtinger representation. The method is first given by Wirtinger, and it's a very natural one. So we start with a projection of a knot onto the plane. And first take a look at those path. It doesn't circle around any part of the knot, so we can continue to deform it onto the point. And that path, therefore, is actually the identity element of our group. But we cannot do the same thing with that one, because it winds around the knot. And you can see that any loop that starts and travels exactly once with the same direction with that curve is equivalent to that curve, that path. So we associate each arc with a loop that starts from x0 and travels exactly once around that loop with the specified orientation. And in this case, there are three arcs divided by the 3 crossing points. So there will be 3 non-trivial elements of our group. And any other loop in that space can be expressed as a combination of those 3. Therefore, we call those 3 the generators of our fundamental loop. But unlike the torus case, in this picture, there must be some relations between the paths coming from the crossing points. And let's take a closer look at this crossing point. So, and I will label the paths with their name of the arcs. So this one called x3, this path, and this one will be called x3, x2, and this one will be called x1. So in the crossing point, there are three loops around it, and you can see that the first taking the path x1 and then the path x3 is equivalent to the first taking the path x2 and then x1. So this crossing point gives a relation something like this. And we can repeat the same procedure at the remaining crossing points, and that will give us two other relations. So we can write the fundamental group of the complement of Terrafoil as follows. There are 3 generators, and there are 3 relations. Using this relation, first I express x3 in terms of x1 and x2, and then the group would look like something like this. There are 2 generators and 1 relation, and you can see that the square of the left-hand side can be written as x1, x2, x1, and x2, x1, x2. Therefore, I have an equation like this. So I relabel the left-hand side as B and the right-hand side A, and the group will be simplified into this one. 2 generators and 1 relation, but simpler than the above. So the group I obtain in this way, called the Wirtinger representation of the knot group. But as the knot gets complicated, this method will be harder to apply. So for this reason, we can use a different method by using grid diagrams. Instead of starting with a projection of a knot, we start with a grid diagram of a knot. And grid diagram is another way to represent knots. And the grid diagram is a square grid. And there's exactly 1 O and 1 X in each row and each column. And no square is marked with both X and O. Given a grid diagram, the corresponding knot can be drawn as follows. First, we draw oriented segments from X to O in each column. And then we draw oriented segments from O to X in each row, with a convention that the vertical ones are always over the horizontal ones. And then resulting shape will be a knot. And conversely, given a knot, we can easily find the corresponding grid diagram. First, we can put it in a form that consists only of vertical and horizontal segments. And then if a vertical segment is under the horizontal one, we can apply the following move. And then the projection would be ready to transform into a grid diagram. So here's an example of a figure 8 knot. First, we deformed it in a way that it only consists of horizontal and vertical lines. Then we modify the crossing points if necessary. Here we applied this part and this part. And then we label the corners as X and O. And the resulting grid diagram would look like this. So, and if we are given a grid diagram, the knot group can be computed as following. First, there's a generator corresponding to each column. So in this case, we have an n by n grid. Therefore, we would have a n many generators. And there's a relation corresponding to each horizontal line that separates the rows. So in this case, there are n by n grids. So there will be a n minus 1 relations, and each jth relation is the product of the generators corresponding to those vertical segments which meet the jth horizontal line. So for example, the first relation is x1 times xn equals 1, because the x1 and xn are the only vertical lines that meets with first line. And the other ones can be written similarly. So let's compute the trefoil, but this time using grid diagram technique. So this is the grid representation of trefoil, and I draw the line segments. So first relation is the product of the generators that meets with that line. So there's only first and third one meets with that line. So the first relation will be x1 times x3 equals 1. And if you look at the vertical segments that meets with the second line, there are 4 of them. So the second relation is x1 to the x4 equals 1, and the other ones are computed similarly. So with this set of relation, I can express x3 as a inverse of x1, and then I can use that to express x4 as a combination, in terms of x1 and x2, and then x5 in terms of x1 and x2, and that is the only remaining relation. So applying those will give the same result, and I can name the left hand side by A and the right hand side by B, and the resulting group will be the same as expected. So, and this is the computation of a fundamental group of complement of a knot by grid diagram. Its advantage over the Wirtinger representation is that it gives a more algorithmic way to compute them, and as the size increases, the method never gets more difficult than that. So as a final point, I would like to talk briefly about how we completed in DRP with Hakan Hoca and some future directions that follows our work. So first, there's a specific family of knots called Taurus nuts, which knot lies on the surface of a torus, and this index indicates the number of times that the nut circles around the torus in the longitudinal way. And the other one indicates the number of times that nut circles around the torus in the other way. So their grid diagrams have an easy representation. This is a grid representation of a PQ nut. And there are p-axis on the left bottom, left corner. And there are q-axis on the right side. And the main diagonal is full of O's. So what we did is we write down the set of relations for the general tape PQ torus case, and then find a simple, and then find a convenient way of relabeling the products. Simplify. We then make it to simplify the nut group as this, which is a fundamental group of PQ torus nut. And the other thing we do is that we try to write a software program, Python code, to compute those relations. And the future plan is to compute the nut groups of us larger nuts by using those programs and the insights we gained from the computations we made in past 2 months. And that's the end of my talk. I would like to thank the organizers and my mentor for their time and efforts, and thank you for listening.